So this is week 14, right? Next week we have one more week, two more classes. Two more classes where I will wait until next week we start talking about this. Okay. Yeah. Good afternoon. Good afternoon. Let me start recording. Did I forget anything? Yeah. Good afternoon, everyone. Okay, so we have been talking about the Heisenberg picture, right? And we wanted to solve an example of the free particle. So we kind of, hello, test. Why is this something weird? Yeah, next week is the final week. Time goes by very fast, right? Yeah, it's generally this is the experience in university. Semester always runs very fast. So yes, today we will finish off the final topic. Actually, just a little bit more. So we're gonna finish this very quickly, and we will have a bit of extra time today. So I'm gonna just because this is a chapter for an example of a free particle. So what we're going to do is, since we're in chapter 7 and it's about a free particle, so we will solve the free particle problem using the Heisenberg picture and the Heisenberg equations, right? And then we try to calculate the uncertainty principle based on this solution. And to demonstrate what is the advantages of using the Heisenberg picture, we will solve this question again using the methods of chapter 3. So partly we can use it like a revision, partly we can see why sometimes Heisenberg picture makes our life so much easier. Okay, so going to the free particle, right? Let us remind ourselves a few things that we mentioned last time. Free particle is where the potential energy is 0. So therefore the Hamiltonian only has the kinetic energy. So it is 1 over 2m momentum operator square. Okay, and then we have derived the Heisenberg equation in the previous Monday class already. So now that we got a chance, I will do this again by the second version of the Heisenberg equation. So now we shall use the second version of the Heisenberg equation. What was the second version? Well, the second version is just dx dt is partial h partial p. Okay, so that was so that was the second version. Previously the formula on the right hand side is a commutator, right? But right now we do it in the partial form, and this one will make it even more easier. So the Hamiltonian is just p square. So if I differentiate p, I just get dx dt, right? So I differentiate this, it just get 1 over m p. That's it. So this makes it even more simpler. So that was my first equation for position. How about the momentum differential equation? So the momentum differential equation, there is a minus sign, partial h, partial x now, but there is no x anywhere in the Hamiltonian, so therefore this is 0, right? So the dp dt is 0. So this is my second equation. Okay, this is the second version, and that is similar to the classical Hamiltonian equation. So that it makes it easy to remember. Hamiltonian equation. Okay, so in this one is in theoretical mechanics. The position derivative is partial Hamiltonian partial p, right? And then the momentum time derivative is partial Hamiltonian partial x. So that is for classical mechanics. But it turns out that in the Heisenberg picture, all we need to do is the same equation but change it into operators. So that is one interesting feature that is connecting quantum mechanics back to classical mechanics. Okay, so we want to solve this solution, right? And we recognize that this equation 2, just tells us that momentum is constant. So that p is constant. So since p is a constant, that means the p of t is always the same p all the time. right? It's a constant. And now we know p, so we can substitute this p into here. That means it's also a constant, so we substitute into equation 1. Okay, so putting this into equation 1, we got dx dt is 1 over m, and then it's just another constant. So, but this one means the time derivative of x is a constant. So if the antiderivative, right, if I integrate this, I will get 1 over m. Wait a minute. Wait, now I notice there's something wrong. What was the equation? One over m. Okay, yeah, so it's 1 over m, p0 t, and then plus the initial momentum. Okay, so we got the two solutions already. P is a constant, and then this thing is a constant. Now, what we wanted to do, I mentioned in the beginning, was to calculate the uncertainty principle, right? So that means eventually I will need to know what is the square of this operator. So the square of this operator is just t square over m square, okay, p, right? And then plus, so plus t over m, right? And then the operators do not commute, so I cannot add these two together. I need to write the distinction xppm, right? So we got this now, and then plus x0 square. Okay. Yeah, wait a minute. I realized that there's something wrong in my calculation. P. Wait, let me double check. I think the first P0 term should be square. Yes, correct. There should be a square. And then let me double check something as well. Because this is the, if I continue with the mistake, then the mistake will get even worse. Hang on. Okay, so actually it's correct, but suddenly I have a feeling that there should be a 2 over here, but there shouldn't be, right? So anyway, let's continue first. Yeah, sorry. You know, I kind of mentioned this in other classes before. Like, sometimes when you calculate something, if you got some experience, right, you kind of develop a spider sense, and somehow your brain subconsciously can tell you, okay, this equation is not right, and then it will help you detect the mistake, and suddenly my spider sense was alarm bell was ringing, but I can't find what was wrong, so it could be a false alarm. Okay, but what we want to do, right, is to calculate the uncertainties. Okay, so the uncertainties, that means I want to calculate what is the uncertainty in x. Okay, and we define the uncertainty as usual. It is the expectation of the operator square minus the expectation of it, and then you square outside, and then you take the square root. Okay, so what that means we need to know what are these quantities. So that means let us calculate what is the expectation of x squared. So that means all we need to do is we just need to square this thing, right? So if we square this, we got all this stuff over here. So we got equals to t square over m square, right? Momentum square plus t over m expectation value. Okay, so expectation value of this is a linear calculation, so everything is expectation value. So we just get px xp, right? And then x plus expectation value x squared at the back. And similarly, I also want to know what is my expectation value of momentum. But momentum is a constant, so this part is easy, right? So this is p0 square, okay? And then this xt is also something that we need. We square it on the outside, right? So we're squaring it on the outside. This means my x was this thing. So what we have here is t over m expectation p plus expectation x, and then you square this, right? But right now, after you take the expectation value, the result is a number. These are not operators anymore. So you can swap the order if you want. T square over m square, p square, right? And then plus 2t over m px, right? And then plus x square, okay? And then I want to calculate this thing, right? So the uncertainty, let's take out the square root first, and then we do the square root later. It's just this thing plus this thing. So it's this term, t square over m square plus t over m px plus xp, and then plus expectation x square, and then plus minus all these things. So minus t square over m square expectation outside, right? Minus 2t over m px minus x expectation outside. Okay, so let us keep the coefficients of t. So the first term is t square over m square bracket expectation p square minus expectation p the square outside. Okay, and this term is the variance or the uncertainty square of the position at the initial time. And then the linear term is t over m. So let's take out the 2t over m outside, and therefore I got half px plus xp. Okay, and then this term is minus px. Okay, so this was where we stopped in the last class, right? This is what we call the momentum position correlation. Okay, so that was where we left off last time. Okay, so now what we want to do is to calculate the result for this particular solution. So this function of t arises because we were solving this Heisenberg equation. And where did our Heisenberg equation come from? We substituted v is equals to 0. So this solution is unique for the case of the free particle. And this equation tells us how the uncertainty changes. If you take the square root, how the uncertainty changes as time evolves. Okay, so pretty much that's it. Okay, so but now we want to calculate them explicitly. And firstly, let's look at this term for a little bit. There is a px xp, right? We can try to simplify this a little bit, because what we can use is the commutators xp. So xp is IH bar identity, right? And the definition of commutator is xp px. Okay, so therefore I can substitute px as xp minus IH bar of the identity. Okay, so my uncertainty momentum correlation is, well, if I substitute the px into this expression, I got xp minus IH bar identity, and then plus xp, right? And then I got minus px over here. So this is half, this is 2xp minus half IH bar expectation identity. Expectation identity, whatever the state is just 1, right? Okay, so I can cancel the 2, so this is just xp, and then minus half IH bar, and then minus px. Okay, so we have simplified this equation already. So therefore, let's put this back in. Our delta x as a function of time and square is t square over m square bracket p square minus p0 square plus x square minus x0 square, and then the c is just 2t over m, and then the whole thing is just xp minus half IH bar minus px. Okay, so we come to this situation, and that is as far as we go because we have not specified what is the initial condition. So initial condition here means what happened at time 0. So at time 0 my momentum is some arbitrary momentum, so we need to specify, right? So this is why we go to a specific example. Yeah, Peter Tingle sounds very weird, but that's exactly what it means. So the new Spider-Man is out now, right? So people must be someone have been watching it right now. Okay, so let us consider an example like the situation where the initial state is given to be this, right? So I got initial state at the Gaussian. So it's a Gaussian distribution, e to the minus ax squared. Okay, so when this is my initial state, well, given this initial state, I can calculate all this thing, right? So I can calculate all this thing, and then I can determine how my uncertainty changes over time. Okay, so let's start with the following. Okay, so what is the initial expectation value of the position? So we use this wave function, and we use our standard formula, right? It's just the integral of x integral, and then the wave position, and then the wave function modulus square, right? So this is the function position. Given the wave function, this is how you calculate the expectation value of position. And my wave function is this. So everything here is real, right? So the square of this, so I can take out this is this thing to the power 2 is give me 1/2, right? And then this becomes the integral from infinity to infinity x, and then this thing twice, so it's minus 2ax square. Integrate this with respect to dx. But when you look at this, you don't need to integrate. The answer is 0 because this is an odd function. So when you have an odd function and you integrate, you're going to get 0. Okay, so this part settled. How about the momentum? Okay, so for the momentum, let's see. For the momentum, expectation of momentum is this one, right? And what is the formula to calculate momentum expectation value? Well, you take the complex conjugate and then sandwich between the momentum acting on the state. Now, the momentum acting on the state in the language of the position wave function is the derivative. So you got this, right? Remember, I hope. Okay, so what you get here is from infinity to infinity dx. The wave function conjugate is 2a over pi 1 over 4 e to the minus ax squared. So everyone here are real numbers. And then I got h bar over I, and then I differentiate this wave function. So differentiating this wave function, I got another copy of the normalization. Differentiating give me my 2ax e to the minus ax squared, right? But if you simplify, you recognize that this is h bar over I, there's a negative 2a, there's a 2a over pi. Now it becomes power half, but I am integrating x e to the power of 2ax squared. Still an odd function, so it's still 0. Okay, So now I know this term is 0, this term is 0. These two are also 0. Okay. Then what about the other ones? Okay, so the other ones are the following. Okay, so let me check my result. Oh, okay. I think I see what happened now. Never mind. It's correct. It's correct. So now what else do we need is I need to know what is my what else do we need? I need to know what is the XP also. So to calculate XP, what is XP? What is the expectation value of X times P? Right. That means this is position. So if you not clear, we can do this, right? So if I do this in the position wave function form, the sandwich is my wave function complex conjugate, right? And then I got the x here. So I got the x here, and then I got h bar over I, and then taking the derivative. Okay, and I integrate this with respect to dx. So this is, if you recall last time, the reason why position and momentum do not commute is if you do the derivative outside, right, because of the product rule, there's a difference here. Okay, so the difference actually is related to the product rule. But let's calculate this. So there's a constant h bar over I. Let me take out the factor, right? And this conjugate is still this thing exponential. This one will have another factor. So I got 2a over pi half. Okay, and then I integral dx, and then the exponential remains inside, and then I got the x here, and then I got the derivative of the function. So I got 2ax e to the minus ax squared. Okay, so this is where we have to be careful. So let's try to simplify this. The minus 2a, I can take it out. So h bar over I, 2a over pi half, and then minus 2a, infinity to infinity. So I got x times x, there is an x square, e to the power of minus 2ax squared. And I want to integrate this with respect to dx. So this is an even function. The integral is not 0. Okay. So if you read the chapter 7 example, it mentioned that this was a question that will appear in tutorial 3. So partially, I'm also solving tutorial 3 together as well, right? What is this integral? So you look at the formula list in the lecture notes, right? Over here, we got a few Gaussian integrals. So we're gonna make use of this. So in particular, right? Let me just copy down the integral. So the integral that we want to use is what happens if I want to integrate x to the power 2. So if I substitute n equals to 1 here, right? So x squared e to the minus x squared, and then divided by some constant square. The answer was, if you copy the formula list, it was for arbitrary n, but you substitute n equals to 1, you got this thing to the power 3. But there's a 2, 2, and 2 to the power 3 here. After you've simplified, this becomes pi over 2 sigma to the power 3. Okay. Now for this problem, my sigma, my 1 over sigma square is 2a. So therefore my sigma itself is 1 over 2a square root. Right. So I use this as my sigma. So therefore my expectation value of xp is equals to h bar over I, 2a over pi half 2a, and then the integral was square root pi over 2. Sigma to the power 3, that means this thing to the power 3, 1 over root 2a to the power 3. And then we got a bunch of stuff here. It's very messy, but so we have to tidy up the messiness, right? So we got square root pi over 2. This thing to the power 3, so is 2a, and then 2a, 2a. So this whole thing becomes bracket 2a. Okay, so now if we put it this way, right, we have some simplifications. Okay, cancel, cancel. And in fact, 2a cancels with 2a, there's a minus 1, right? So if I bring the I upstairs, I got I h bar minus 1, and then after cancel everything is left with half. So at the end of the day, this is I h bar half. Okay, so I have found the expectation value of xp already. Okay, so now I found expectation value xp. What is this answer? I can substitute this already. So the correlation is C0 is supposed to be xp, right, minus half I h bar minus p minus expectation x. But we have found this is I h bar over 2 minus half I h bar. This is just 0 times 0. So actually cancel 0. So initially this is 0. So we settle this part. Okay, so the answer is just 0. At the end of the day, suddenly everything becomes 0. Okay, so we done that. So this part settled. Right, so we just need to figure out what are the remaining terms over here. So what is momentum square and x square? Expectations. So let's do that now. Okay, so yeah, am I going too fast? Does anyone have any question? Yes. So based on our calculation, yeah, it can be complex, but luckily they cancel with it itself and it becomes 0, so there's no complex number. Yeah, so the Gaussian integrals, right? So let us face our that is what we want to do today. We face our fears head on. Yes, this is by assumption. Yeah, so we are given if the particle, this is a situation where the initial state is Gaussian. So the question gave you this. Okay, so the question gave you this, and we just need to calculate what happens at a later time. So there's going to be more horrifying integrals. Let's do that straight. Let's do that directly. So the next thing we want to do is expectation value of x squared, right? So what's the expectation of x squared? Well, this is a wave function conjugate x squared and x, right? And my solution was 2a over pi, power 1/4, square this so it becomes power half. And then this is the integral of x squared of 2 exponential, so it becomes 2ax squared. Okay, so it's 2ax squared. Okay, so 2ax squared. And then, yeah, this is another integral, right? But it's the same integral as before. So the answer is just root pi over 2, 1 over 2a, and then another 2a, right? So this is the same as before. Therefore, I got 2a over pi square root. And then the answer is root this over 2, right? And then I got 1 over 2a, and then another 2a. So the square root 2a cancel. This thing cancel. And everything is left behind with 1 over 4a. So this is the expectation value of x squared. Now, the next thing is the expectation value of momentum square. Right? So momentum square now, what's the expectation of momentum square? It is the integral of wave function, right? This is the bra. And then this is the momentum acting on the cat twice. Right, so this is acting on the state twice. So that means the momentum operator on the wave function becomes the derivative operator. So it's acting twice on my state here, and this becomes wave function. And then this thing, if I square this becomes negative h bar square, and this becomes the second derivative of my function. Okay. So taking the h bar square outside, right? And then the normalization factor is the same, so it's just 2a over pi. Take out twice of them is half. So I'm integral with respect to dx, e to the power of ax square the constants I take it out, and then the terms that need to be differentiated is I need to differentiate e to the minus ax square twice. Okay, so this is another horribleness that you need to deal with. So we need to figure out how to differentiate this, right? So firstly, let's differentiate one time. Okay, so differentiate one time, it becomes minus 2ax e to the ax square, and then you differentiate again. I got a product rule this time. So the first term is minus 2a e to the ax square, and then I got 2ax. Differentiate the exponential, giving me another 2ax come out. So you got ax square, right? So the front minus minus becomes plus 4a square x square e to the ax square minus 2a e ax square. Okay, so what I get here is now this is minus h bar square 2a over pi to the power half, and then integral with respect to dx, a bunch of stuff. So there is a factor of eax. I multiply inside, and everyone becomes 4a square x square e to the power minus 2 ax square minus 2a e minus 2 ax square. Okay, so I got two integrals this time. So let's try to split it up. Right, so the first term is h bar square 2a over pi half. So this term, there's a 4a square, so let's put the 4a square outside, and then I'm integrating x square e to the 2ax square dx, right? And then the second term becomes a plus h bar square 2a over pi half 2a integral of e to ax square dx, right? Both are from infinity to infinity. So you just need to work out this integral. Okay. Well, this part is the same integral we have been doing. So it's still the same. So it's pi half 1 over 2a root, and then another 2a. Okay, so this part is done. This part, let us use the formula. So the Gaussian formula with no x in front, the Gaussian integral. So the Gaussian integral gives what is the integral from e infinity to infinity, e to the something square with dx. It just gives me square root pi over alpha, right? But this time my alpha is 2a. Okay, so the answer is pi over 2a. Okay, so this integral is pi over 2a. So let's put everything in. So my expectation value of momentum square is equals to minus h bar square 2a over pi. This is square root. There's a 4a square. There's a root pi over 2. 1 over 2a root 2a. And then the second term is h bar square 2a over pi half 2a. And then this is pi over 2a square root. Okay. So again, there's a lot of horrifying stuff, like you said, but there's also a lot of cancellation. This thing cancel, this thing cancel, right? And then let's see, 2 cancel, right? And then must be careful. There's 1a like this. So the first term is minus h bar square a, right? And then this thing also cancel 2a, square root pi also cancel, and then this is 2a. Yeah. Cancel culture gone mad, people say. Which is this, for physics is this doing this. So 2h bar minus this is just positive h bar square a. Okay. So we have found this already. So now we can calculate the uncertainty square. Delta x t square is, where was my uncertainty formulas? It's over here, right? So since it's here, let's put it in straight away. P square is h bar square, so this is t square over m, and then this is h bar square a, minus 0, so this part is done, and then uncertainty of x squared, where was it? We just got it just now. It's 1 over 4a. So this part is 1 over 4a. This term is 0. And 2t over m, this is the correlation. We have also found that the correlation is 0. So at the end of the day, what we have is 1 over 4a plus h bar square a t square over m square. So if I take out 1 over 4a, this becomes 1 plus 4a square h bar square, right? T square over m square. So I got the delta x finally. So the uncertainty itself is taking the square root. So I got 1 over 2 root a, 1 plus 4a square h bar square t square over m square. Okay. So that was the uncertainty, and we can now check the uncertainty principle because we have the momentum p. This one is easy, right? What was this? This was delta p square, right, minus delta p and then the square outside. We know that this term is 0. This term we have also calculated. This is h bar square. So h bar square a square root. So this is equals to root a h bar. Okay, so now we got we have the two uncertainties, so we can check the uncertainty principle. Okay, so this is delta x at time t. The uncertainty at time t is this times this. So it's just equals to h bar times 1 over 2 root a square root 1 plus 4a square h bar square t square over m square. So the root a cancel here, and we find that this is h bar over 2, right? And then with 1 plus 4a square h square t square over m square. So remember what was our uncertainty principle? Uncertainty principle is delta x delta p must be greater or equals to h bar over 2. So it is satisfied. At time 0, it is the minimum uncertainty, but as time goes on, the uncertainty becomes more and more. So that was our result that we got here. Okay. Yep. Essentially, we are done with this example. Any question? I'm sure I made better jokes than this. Lame joke just now. For 5, okay, so this is page 5. We have found this uncertainty. This was for a, remember, this is for a particle initially with Gaussian probability distribution. Okay, and if you start with some other probability distribution, then your results might be different because we calculated this using the exponential and then we got this result. So if it's some other function, then you will get some other answers over here. The time influences uncertainty. Yes, in that sense, as you can see, right? Yeah, this is the time dependence of our uncertainty. So our uncertainty in x, right, at time 0, our uncertainty x is 1 over square root a. Okay, 1 over square root a. If you remember the Gaussian probability distribution, if you learn the statistics in the Gaussian, right, square root a is the standard. Half square root a is the standard deviation of a Gaussian curve, right? So so that was at time 0, and then as you can see, as time increases, the wave function starts to spread because your standard deviation will start to spread. We will analyze this in more detail after this, but from here you can already see the uncertainty grows large. But for momentum, it seems like momentum uncertainty remains the same. It kind of similar to what we expect of conservation of momentum, right? For a free particle, no external force, even though we do not expect Newtonian mechanics to be here, but for here is satisfied. Yeah, momentum uncertainty remains the same, so anything about momentum remains constant. Even the operator is constant. Okay, yeah. Any questions so far? Seems to be the case, yes. So if you put a system for a long time, yeah, the uncertainty starts to, at least for the case of the free particle. Why? Because for a free particle, there is no potential, there's no force. So you just put a particle there and then you just let it go, right? Yes, uncertainty will become big, okay? But if it's an infinite, for example, if the infinite well, if you put a particle there, then you're sure that is within the well. So it depends on the potential, but from here is similar to our imagination. But put it for a long time, if it's a flat surface, we put a particle on a flat surface and then you let it go, after a while you don't know where it is. The position at least. Momentum, you know, but position less and less certain. Okay, so we are done with we are done with the Heisenberg picture. So as I said, we have finished chapter 7. That was the last thing from chapter 7 already. Chapter 8 will not be covered in the exam. So we will just introduce a few concepts about what people are doing. So we will talk about entanglement and things like that for next week. But for now, we do a few more horrible integrations. Okay, so what we're going to do is we're going to study the free particle again. Okay, but using wave functions. So this is partially like a revision of what we did last time, but now this is same problem, so we are using to solving the same problem using this and different methods. Yeah, I guess so. If we left the cat in the box, correct. Yeah. Is there any example to show that? Well, I mean, in some sense, this is an example, a free particle, right? Free is like exactly just put a particle, like nothing special about it, right? We don't need to convert this into some spin or something. It's just a particle with position, right? And let's say if the initial probability distribution is the Gaussian, right? If you release it, then the uncertainty spreads. So there's not much example other than doing the experiment. So if you let it go, and if you measure the position at 5 seconds later, or measure the position at 100 seconds later, the uncertainty just becomes bigger and bigger. Yeah, correct. Basically, free particle will get lost. Yes, also correct. The wave function does not collapse. Yeah, because if you remember, right, the wave function tells us the probability distribution of measurement. Once you measure it, you get the outcome. Then you know, oh, the particle is here. The reason why it's uncertainty is because if you prepare many identical states, right, and then 5 different people measure the same situation, the 5 different people may get a different result, and the different result will give you the distribution. That's why that is the uncertainty. So if the particle is very certain, right, that means 5 different people measure around the same value. So that is the statistics aspects about it. I guess you can think of it that way, but that is not a quantum That's a classical example, right? Okay, so the point of this part, what time is it? So the point of this part mainly is to show you the advantage of using the Heisenberg picture. Therefore, we will try to do this using wave function, and then you realize that, wow, the equation becomes extremely ugly as we will do this, right? Just now we did a bit of effort, right? We do Gaussian integral, but the time dependence part is very easy. If you do it using wave function, right? Let's see, I will show you. It's gonna get very ugly. Okay, so that is the point of this exercise. So let me remind you before we start, right? We should revise a little bit in position representation. Right, the Schrodinger equation was the wave function psi d dt, right? And then on the right hand side is the Hamiltonian. If you write it in position, that means this Hamiltonian is p square is the second derivative h bar square, right? And then plus the potential, and then acting on the state psi, right? We have done this in chapter 3. We did separation of variables, and we have found that my wave function x of t can be separated into the exponential of iet over h bar psi x, right? And this wave function is obeying this equation. So this is h bar square over 2m second derivative plus v psi is equals to e psi. And in particular, this psi is the eigen state of the Hamiltonian. So this is the Hamiltonian operator, right? Just a bit of revision, nothing special over here. But what we did was, in chapter 3, there was an example of a free particle. Okay, so free particle is v equals to 0. So if I want to find the eigenstates of this situation, I end up with this differential equation. So I bring this becomes 2me over h bar squared per psi, right? And then my solution that I got was a constant, and then e to the power of ikx, right? There's a negative also, but it's just another k. So generally speaking, this is our a solution for a particular k, right? Where this k is 2me over h bar. So that means this solution corresponds to this energy. And if I express in terms of energy, I just square both sides and solve for E. I got k squared h bar squared over 2m. So this is one eigenstate with this energy. Other k gives you other eigenstates with other energies. Okay. So if we put this back into our time-dependent wave function, we got what? So we got the a and then e ikx, and then minus ie t over h bar, and then my e is given by this. So we have found that this is e. I take out the I, and then I got kx minus the e is this thing, right? So it's e k squared h bar t over 2m, right? Yeah, so we have gotten this, and this was if you recall what you did in mechanics and electromagnetism, this is a wave solution where kx minus omega t, right, where my omega is k squared h bar over 2m. Okay, so from here you can derive the de Broglie relation over here. Okay, your function is a constant. Now, what was the situation that we encountered last time? When we got the wave function, right, normally what we try to do is we try to normalize it, but when we try to normalize it, you cannot, it's infinity. So the problem, so individually it cannot be normalized. The problem is for a single k, the solution, the wave function is not normalizable. So we create normalizable wave functions by superposition of various k. Right? Superposition means you add up a few functions, and then how much of this function you add to how much of other functions. What is the recipe? What is the ratio of all the functions that you add? What is the proportion? Those are the coefficients, right? So for the discrete states, you sum, but here is continuous. Therefore, you integrate. So the way to do it is you integrate with respect to k, with some coefficients that depending on k, and then I got e to the I kx minus k squared h bar t over 2m, right? So I superpose different k into our solutions, okay? And then this fk depends on the initial condition, right? So to fix the solution, it depends on the initial condition. So we choose initial condition, initial wave function at time 0. So at time 0, we just x0, right? So at time 0, this term is gone. So to fix fk, right, and then integral fk, and then e to the ikx. So this is actually a Fourier transform of the k, right? So this one is depends on initial condition. And then so the initial condition will tell you what this function is. Our example is Gaussian. So if my probability distribution is initially some Gaussian, then after that we will use the Plancherel's theorem to identify what is my f of k. So f of k is the inverse Fourier transform. Rather, this is the Fourier transform and this is the inverse Fourier transform. So this is integral over x psi of x0 e to the minus ikx. Okay, so that was the procedure to figure out what is my wave function given some initial configuration. Okay, so yeah, so we are studying the case. What time is it now? Should we take a break? A bit later, a bit more, right? Studying the case where the probability, where the distribution is initially Gaussian. Okay, so that means at time 0, it was 2a over pi. Actually, we did solve this before last time, right? Minus ax squared. Okay, so this is just the wave function. To get the probability distribution, you need to take the this thing square, right? So this thing squared becomes 2a over pi square root e to the minus 2ax squared, and then the probability distribution is the Gaussian. Right, so it's something like this, the bell curve. So the larger the a, the wider this function is. The smaller the a, the sharper it is. Okay, that's why the a is the standard deviation and also the uncertainty. Okay. Oh no. Okay. Right, so this is my initial wave function. How to get fk? We use the Plancherel's theorem. Right, so we got this initial, and then let me write out the thing. If you, just in case you're confused, what is going on. So now I want to determine what is my wave function at later time t. So x of t, right, it is supposed to be 1 over 2 pi integral of infinity to infinity dk f of k e to the I kx minus k square h bar square t over 2m. Okay, so that means I need to know, I need this. So I can calculate this using the Plancherel's theorem. Which is 1 over 2 pi square root the integral from infinity to infinity and then dx, my wave function at time 0, e to the minus ikx. Okay, so I need to do this in order to figure out what is my fk, and then I need to get my wave function at a later time t. What you mean last page? You mean this? I kind of, this is fast because this is a repetition of what we did in chapter 3, right? But this part is new. Okay, so now I will go a bit slower. In fact, yeah, I don't know if we can even finish everything today or not if I go a bit slower, but let's see what we can do. Okay, so anyway, we want to determine the f of k, right? So the f of k is 1 over 2 pi, and then this integral now. So this integral is the integral from infinity to infinity. My wave function at time 0 is over here, right? It's over here. So let's put the wave function in, which is just 2a over pi 1/4, and then this is e to the minus ax square, and then at the back is just ikx. Okay, so what we have here is a bunch of constants which I can take it out. Okay, and then this is e to the minus ax square minus ikx, and then integrating with respect to dx. So this is another integral which is given in the formula list, but let me put it here, right? So the integral was the following, is e to the alpha x square plus beta x, integrate this with respect to dx. This is equals to root pi over alpha e to the power of beta square over 4 alpha. Okay, so this is the same as this integral, where my alpha, if you compare, right, my alpha is a and my beta is plus, this is minus, so it's negative ik. Okay, so I plug this in, right? So if I plug this in, what I got here is just root pi over a e to the beta square. So beta square is ik square, so I got negative k square over 4a again, right? So my f of k is equals to 1 over 2 pi 2a over pi 1/4 power, and then this becomes pi over a, and then e to the minus k square over 4a. Okay, so let's see what do we have. The square root pi cancel, right? Now it's a bit messy because this is power 1/4, this is power a, so just to be careful, let me write everything carefully. So this to the power minus half, this is 2a to the power 1/4, this is pi to the power 1/4, and e to the k square over 4a, right? So I got 2a, this and this becomes minus 1/4, pi minus 1/4, e to the k square over 4a, right? So both are 1/4, so I can just put this together. This is 2 pi a to the power of 1/4 e to the power of k square over 4a. So using the Plancherel theorem, I have determined f of k already. So now I know what is my f of k. I got this. So now I know my wave function at the later time t. Right? So what's my wave function at time t? So in the front, we had 1 over root 2 pi. And then I'm integrating with respect to k, right? And then my f of k is this. E to the power of k squared over 4a. And then e to the I kx minus k squared h bar t over 2m. Okay, so now my variable of integration is k. So you look at the k, there's a k square here, there's a k here. So let's try to group the coefficients together. Firstly, I will take it out, take the constants out. This is root 2 pi. This is 2 pi a to the power of 1/4. Negative, so I put it downstairs. And then over here, look, there's a k squared. So I put the coefficients of k squared together. So I got minus I h bar t over 2m minus 1 over 4a. So all these are coefficients of k squared. And then this is coefficient of k power 1 minus ix k. And I integrate this with respect to k. Okay, so let's try to work out this integral. So 1 over 2 pi. So you see, right, now you already feel, wow, Heisenberg picture, isn't it much better to determine the time dependence of some uncertainty, because I want to derive the same result using wave functions to show you how what a nightmare this is. So taking this out, right, so I got taking out, and then I got 1 over 4a. This is a complex number where this is the real part and this is the imaginary part, IHT over 2m. And then this is k squared, and then this is plus ix k. Okay, so again, I can still use this integral, right? It's the same form, where this time my alpha is this bunch of stuff. So 4a plus I h bar t over 2m. Beta is ix. Okay, so if I put everything in, the answer is pi over root alpha, right? So pi over the alpha. So all this rubbish here is alpha. And then the whole thing is square root. And then e to the power beta squared. So beta squared becomes negative x squared over 4 alpha. So this alpha is all this thing here, which is another mess. Okay, so let's try to collect everything together. But at least we know, after all this difficulty, this is how the wave function changes with time. Right, so 2 pi root 2 pi a to the power of 1/4. Right, and then after I integrate, I end up with this. And then this part, let's multiply the 4 inside. So this is x squared over 1 over a. And then if I put the 4 inside, it becomes 2i h bar t over m. Okay, so you see it's so ugly, right? This part, let me tidy up one more step. This part, let me put the 4a upstairs. So if I put the 4a upstairs, I got 4 pi a divided by 1 plus, putting the 4a upstairs, I got 2i a h t over m square root. Okay, so there's a root pi, and root pi will cancel. Root 2 will cancel this, it will becomes a 2. So my wave function now, trying to like simplify this as much as I can, I got 2 pi a to the 1/4. This is the square root of 2a. The downstairs is 1 over 2i a h bar t over m square root. Okay, and then this part also, let's take the a upstairs. So I got ax squared. So this becomes 1 plus 2i a h bar t over m. So notice that this part is the same number as this part. Okay, so at least now we sort of know we are on the right track. Okay, now there's a, hang on a minute, there's a 2a and then there's a 2a, but this is the different power. So square root of 2a is just this thing twice. Okay, so I can cancel one of these, right? And then this part is the same, so I'm too lazy to write everything again, but basically this turns into 2a over pi to the power of 1/4, and then this is 1 over the square root of all this stuff, and then this is e to the power of ax squared over 1 plus 2i a h bar t over m. Okay, so this number is the same as this number. So finally we have found the uncertainty at time t. Okay, any questions so far? B equals to positive ix, yes, positive ix. Yeah. So we are using this integral here. This last term here. Beta. What is it? What time is it now? Wow, it's 5:06. Okay, I don't think we can finish everything today, but let's take a break and let's see how far we can go. Oh, look. I'm recording here. Okay, good. So for the p in this form, right? For the p in this form, for the wave function in this form, I got psi x of t. This is the b, and that's e minus lambda x squared. Okay. So later I will need to calculate a bunch of stuff. So what is lambda complex conjugate? Lambda complex conjugate is b conjugate minus lambda conjugate x squared. Okay. And then also if I want to do this thing square, so it's just this conjugate times itself. So this is just b conjugate square e to the power of lambda bar x square, and then e to the minus lambda x square. So this is actually b square e to the minus lambda conjugate plus lambda x square. So we're going to use this later. And we will also need the derivatives. So let us differentiate this with respect to x. So if I differentiate this with respect to x, right, the x dependence is here. All this doesn't depend on x. So if I differentiate with respect to x, firstly I got minus 2 lambda x e to the minus lambda x squared. So simplifying, I got 2b lambda x e to the lambda x squared, right? And then if I do the second derivative, okay, I will get, well, I got a b here, and then chain product rule. So the b, I got 2 lambda e to the minus lambda x squared, and then I got minus 2 lambda x. Differentiating this gives me another 2 lambda x e to the minus lambda x squared. So if I simplify this, I will get b e minus lambda x squared. This one will becomes 4 lambda square x squared minus 2 lambda. Okay. Later we'll also need this. Because we need this thing and then the complex conjugate, right? So for lambda, it is a 1 plus 2i a h bar t over m. Therefore, your complex conjugate is a 1 minus 2i a h bar t over m, right? So lambda plus lambda bar is this plus this. We did a similar calculation just now. What we got was 2a 1 plus 4i a h bar t over m. And then we will also need lambda lambda bar multiplied together. This is just a square 1 plus 4i h bar square 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 square. Okay, so we're gonna need this later, right? Need a lot of preparation just to start calculation. But now let us start. What are the uncertainties? So firstly, what is the expectation value of x, right? So the expectation value at time t is this thing. So we need to do this calculation, right? But it's going to be 0 because my wave function was x and then mod b square, right? And then e to the power of minus lambda bar plus lambda x square dx. So all this stuff is an odd function, right? This is x to the power 1. So therefore the expectation value here is 0. Okay. So this is 0. What about the expectation of x squared? So the expectation of x squared is I need to perform this calculation. X squared, sorry. Right? So I need to perform this calculation. So this means this is integral of x squared. Mod this square is mod b square e to the lambda plus lambda bar x square. Integrate this with respect to dx. So I can take the b out. And then I integrate x square e to the lambda plus lambda bar x square. Okay, integrate this with respect to dx. Now, how to do this integral? We use the formula. So the formula was quite very far away by now. So let me put it again here. This is integrating e x squared minus x squared over a square with respect to dx. This gives me root pi over 2, right? And then a to the power 3. So for this case, my a is 1 over lambda plus lambda bar. So this integral is going to be equals to root pi over 2, this thing to the power 3, right? So it is, so this is inverse. So this is lambda to the power of minus half, and then this thing to the power 3. So this to the power 3 over 2, right? Okay, so now we got delta x squared. What time is it now? Yes, the I are somewhere inside, correct. Because see, the I is inside here. My handwriting is too small. Oh, oh, you mean this? No, no, no. Oh yeah, correct. This thing times this, the I disappear. You're right. The I disappear. Right, it's just this multiplied to each other. So 2i times negative I, it will be cancelled. Yeah, you're right. Good point. Okay, so what we have here is x squared is, well, we got mod b square, and then root pi over 2. So let me put everything here first. Okay, and what was modulus b square? So modulus b square, if you recall, right, modulus b square was all this bunch of stuff. So I'm modulus b square. So modulus b square is the front becomes to the power half, and then this becomes square root of 1 plus no more I, h bar square h square t square over m square, right? And then this is root pi over 2, and then lambda plus lambda bar, like you pointed out, no more I, is all this thing to the power 3 over 2. So I got 2a 1 plus 4h bar square a square t square over m square. The whole thing is to the power 3 over 2. Okay, so what do we have? Well, we have some more cancel culture, lambda root lambda, right? And then well, let's keep it like this for now. There's a half, there's a 2a to the power half, right? And then there's another 2a to the power of minus 3 over 2, and then this thing and this thing are the same factor. So this thing is actually 1 over 1 plus 4a square h bar square t square over m square. This is to the power of negative half. This is minus 3 over 2. Okay, So if I simplify this, right, this one becomes minus 4 over 2, which is just hang on. Minus 2. Oh, there's already downstairs, so 1. Yeah, so I want this to be minus 2 over 2, so this becomes minus 1, correct? Right? So these two terms will multiply with each other. Minus 3 over 2 minus half becomes minus 2 over 2, so this becomes 2a to the minus 1. This thing is to the power of minus 1. So if it's to the minus 1 but it's downstairs, so if I flip it, it becomes 1 plus 4a square h bar square t square over m square. Now it becomes to the power of positive 1, right? So finally we got it. This is 1 over 4a, and this is 1 plus 4a square h bar square t square over m square. So this is delta x square. Okay, so yeah, after all this mess, right, after all this ugly calculation, we can finally determine what is my expectation value, which is just delta x square minus delta x, the whole thing, square. Right, just now we found this to be 0. This was over here. So the answer is 1 over 2 root a, and then 1 plus 4 h bar square a square t square over m square square root. Okay, so it is agreeing with what we got just now, right? When we were doing the Heisenberg picture using the operator method, we did calculate this earlier, and we did it much faster, right? So the equation that we got was the same. See, over here. So at least we can confirm our calculation method, right? So if you compare and contrast, maybe you don't like this method. Maybe you find both are also equally messy. I don't know. It depends on your perspective. But the time dependence part is for, if you do the Heisenberg picture, it's so easy, just this thing, right? But when we want to derive the time dependence of this function, we need to get this ugly mess over here. So you need to deal with this ugly mess in order to get the how does the time uncertainty in time changes. For plus also. Wait, correct, right? Sorry, which part is hard to read? Do you want to go back? Any question? Wait, did I mess? Yeah, which part do you want to go? No, don't worry, this is not in the exam. If this is an exam, right, the exam is one question only, because we've been, now it's almost 2 hours. We're calculating this nearly 2 hours. So exam is 2 hours. So if you want this, then the exam is just one question. Then you spend 2 hours doing this. No, impossible. It's not in the exam, but if you do physics research or some other things in the future, then you might encounter this type of situation. Okay, so at least you are prepared for this kind of things. Okay, so for the next thing, let us calculate the uncertainty in momentum. For the uncertainty in momentum, right, if we are in the Schrödinger picture, we can use this theorem. But this term is 0, so the uncertainty in position is 0 over here. Okay, so this part is settled, but the p square is the troublesome one. So the p square is the troublesome one, so we're going to do this soon. Yeah, retake, get it wrong. If this type of exam in quantum mechanics, the exam score is also quantized, right? Only one question, so it's either 100 marks or 0 marks. Maybe you can say calculation, but yeah, there's no such thing for this type of question. No way. So we got this, right? So we got complex conjugate, and then h bar over I operating on this twice. So we got the integral of dx. This thing, I got negative h bar square, second derivative of this. So I pull out the factor of h bar square, integral of dx. This thing is b bar e to the minus lambda bar x square, and then the second time derivative. So the second time derivative we found just now, where was it? So it's b e minus lambda x square 4 lambda square minus 4 lambda. Okay, so this part are constants. I will take them out. I will take out a factor of 2 also. So I got 2h bar square b bar square integral dx. So then let us put this thing together. So this is minus lambda plus lambda bar x square. This is integral 2 lambda square x square minus lambda square. So let us split out the integrations. 2h bar square b square. The first term is 2 lambda square integral x e minus lambda plus lambda bar x square with respect to dx minus wait, this lambda power 1. So this lambda power 1 just e minus lambda bar plus lambda x square. Integrate this with respect to dx. Okay, so again, using the integration formula, this is my 1 over sigma square, right, or 1 over 2a square. So if you work out, this is root pi over 2, then this is what we did just now, so it's to the minus 3 over 2, right? And for this part, this is my Gaussian integral with alpha as lambda plus lambda bar. There is no beta for this problem, so the answer is root pi over lambda plus lambda bar. Okay, so let's see how it looks like once we put everything in. So my expectation p square is negative 2h bar square b square mod, and then this is 2 lambda square. So 2 and this 2 will cancel, so I got root pi lambda square lambda plus lambda bar to the 3 half minus lambda root pi and root this. Okay, can't do much here. Now let's try to simplify. So this is 2h bar square mod b square. Actually there's root pi, so let's take out root pi, and then I got a lambda, right? So this is lambda square to the power of 3 over 2. So to the power of 3 over 2 is lambda plus lambda bar times another lambda lambda bar, right? So this lambda, this is to the power of 3 over 2, and then this is lambda lambda plus lambda square root. So I can factorize a few more things out. Okay, I can take out lambda and lambda plus lambda bar, and then what is inside the bracket is left behind this factor minus 1. Now this part, right, this part you notice is just 1 lambda plus lambda bar minus lambda plus lambda bar lambda plus lambda bar. So these two terms will cancel, and I am left with minus lambda bar lambda plus lambda bar. Okay, so this, the expectation of p squared now is 2h bar square mod b square. Mod b is another bunch of ugly stuff, right? We'll deal with that later. There's a root pi, there's a lambda plus lambda bar square root, negative lambda, and another square root. Wow. Okay, that's no, there's no square root downstairs. Yeah. But there is two negatives, so let's put the negatives together. So I got 2h bar square b square root pi lambda lambda bar. So this is absolute value of lambda, and this is lambda plus lambda bar to the power of 3 over 2. Okay. So let us attempt to put everything back. Okay, so what was the mod b squared? So the mod b squared was, it was over here, so let me put this in. So everything here is becomes 2a over pi square root half, right? And then mod b contains this part, which is 1 plus 4h bar square a square t square over m square. And then there's a root pi over here. Okay, and then the lambda lambda bar is just a square over this thing actually, 1 plus 4h bar square a square t square over m square, right? And then the downstairs to the power of 3 over 2, so to the power of 3 over 2. And then lambda plus lambda bar, what we have found just now, right? We have simplified just now. We have 4 h bar square a square t square over m square. Okay, so it's a bunch of ugly stuff, but look at it. This is to the power 1, this is to the power half, this is to the power minus 3 over 2. So actually this, everyone here cancel each other, right? Pretty interesting, right? And then also square root cancel with square root. So let's see what we have left. This is 2h bar square, there is root 2, and then there's a half, and then I got a square, and then there's a 2 to the power of 3 over 2, and then this is a to the power of 3 over 2. Okay, so this becomes minus 2 over 2. So this becomes minus 2 over 2 minus 1, and then this, so this just left behind with a, right? And then this is half, so it's minus half, so it's minus 2 over 2 is minus 1 again, so it's 2h bar square 2 to the minus 1. So this cancel. So finally at the end of the day, yeah, we found this, right? Okay, so after at the end of the day, if you do everything correctly, you got this. I don't know if you feel tired, but I also feel exhausted doing this calculation. Is it more easier? Maybe, I don't know. You try and see. I didn't think about this. Yeah, so you can, then you can see. So you can cancel in terms of lambda first, right? Because I think, yeah, I see what you mean here. So if you just keep in the form of lambda, good point, right? If you keep it in the form of lambda, then this become this. So this will cancel, right? That's a good idea actually. Yeah, I should have done that. Then it will be so much better. Okay, so yeah, next time the lesson, keep it in terms of lambda. But anyway, we have found the uncertainty of p, expectation of p squared. So therefore the uncertainty of momentum is this thing. But this part is 0, so the answer is just h bar root a. Okay, so it's a constant, right? And the uncertainty in x was this thing, so therefore the uncertainty principle is delta x, delta p, right? So it is just these things. The root a cancel each other, so I got h bar over 2, 1 plus 4h bar square a square t square over m square square root. Yeah, and definitely it's greater than h bar over 2. So finally we have found this. Okay, yes, so that was a good point just now. This is good. So I think that's all. That is finally we have achieved our goal, right? We have for this is one to remind you, this is for the Gaussian case, right? We have done this calculation, we have derived this result using two methods. The first method was using the Schrodinger picture. So when we did the Schrodinger picture, right, we need to do this a little bit first, but this is for time 0. So at time 0, the integral is there, but it can be done, right? And we gotten this result using Schrodinger picture. But if we didn't learn Schrodinger picture, we only know wave functions. Then for the Gaussian, we need to Schrodinger equation, we need to solve the wave function. After we solve the wave function, we need to do the inverse Fourier transform to get the fk, right? So to get the fk, finally getting the fk, we get the time-dependent wave function. After we get a time-dependent wave function, then we got this ugly mess over here, right? And then this one was just to show you the graph. And then we need to calculate the uncertainties. So in order to get the uncertainties, we need to differentiate twice. We get a bunch of constants. We need to do all this. And then we spend all this time calculating. And finally, we got this. Okay? So to me, at least, I feel if we use the Heisenberg picture, it's a bit faster, because to getting the time dependence in the Heisenberg picture is so simple. Doing it in this way, right? Just solving some linear differential equation, settled already. But here, to get the time dependence, first you need to do the Fourier transform, the Plancherel's theorem, all this thing, which is an ugly mess. So yeah, so don't worry. Like I said just now, exam will not have these types of question, but the lesson that we want to convey for today is to, depending on which description, which formalism, some formulation can make it easier to calculate certain things that you want, right? Whether it's a Heisenberg picture or the Schrodinger picture. Okay, so yeah, that's it. We have finished for chapter 7, and it was a revision of chapter 3. Next week we will talk about entanglement.